Hello and welcome. This course is about how artificial intelligence and machine learning are used to design and build and improve semiconductor manufacturing and technology. Over the semester, you'll go from the very basics of machine learning in Python all the way to the models that solve real problems inside modern chip factory or fab. Today's lecture sets the stage, why this field matters, where AI is already being used in chip manufacturing, and a little bit of its history. Let's begin with why chips are worth a whole course. Three kinds of chips carry the entire digital world. Logic chips are the brains that do the computing. DRAM is the fast working memory a computer uses while it is running. And NAND flash is the storage that keeps your data when the power is off. Each of these has improved at an astonishing steady pace for decades. A modern logic chip holds over 200 billion transistors. High bandwidth memory moves more than a terabyte of data per second, and the newest flash stack stacks more than 300 layers and close to 250 terabytes of data. Over the next three slides, we'll look at how each one got there. Here is the logic roadmap. Read it from left to right. The numbers along the top from 180 nanometers down to 3 nanometers are the technology nodes. As features shrank, engineers had to keep reinventing the transistor itself to keep it working. They strained the silicon to speed it up, switched to a new high-K metal gate material, then changed the transistor's shape from flat to a three-dimensional fin, the FinFET, and then wrapped the gate all around the channel with the gate all around and nanosheet designs. And the next steps stack transistors on top of each other with complementary FET or CFET. The takeaway is that every step down this roadmap demanded a brand new device and a brand new manufacturing challenge. DRAM, Dynamic Random Access Memory, tells a similar story. A DRAM cell stores one bit as a little bit of charge on a tiny capacitor, and this roadmap, labeled D3X, D2X down to D1Z, tracks the cell getting smaller and smaller with the numbers showing the shrinking dimensions. To keep printing these tiny features, DRAM now uses extreme UV, the same advanced light source used in the most advanced logic. And the cell design itself is changing from today's conventional layout towards denser cells and eventually true three-dimensional DRAM where cells stack vertically. The point is that even memory, which people picture as simple, is pushing the limits of physics and manufacturing. NAND flash is my favorite example of engineering cleverness. For years, it scaled the old way by shrinking cells in two dimensions. Around 2014, the approach hit a wall, so the industry did something bold. It began stacking cells vertically, building upwards in layers like a high-rise. Look at the pace. The first 3D NAND had 24 layers in 2014. By 2019, it was 118 layers, and today it is around 300. And the roadmap points to more than 1,000 layers by 2030. Altogether, that is roughly a 100,000-fold increase in storage density over 25 years. The lesson: when one path runs out, this industry finds another. Step back from the three products and you'll see one force underneath all of them. This chart plots the number of transistors in a chip over time, and notice the vertical axis is logarithmic. Feature sizes have fallen about 1,000-fold in 50 years, from 10 microns in the early 1970s to about 20 nanometers today. On a logarithmic scale, the straight line like this means exponential progress, steady compounding improvement years after years. Nothing else humanity manufactures has improved this much, this consistently, for this long. The real features in today's transistors are only a handful of atoms across. So how do you actually build the chip? You build it upward in about 100 layers, and each layer is made by repeating the same loop. First, you deposit a thin film of a material, then you pattern it with lithography, printing where the features should go. Then you etch away the material that you don't want, leaving the pattern behind. Then you clean and polish the surface flat, ready for the next layer. Add in steps like ion implantation and heat treatment and run this loop about 100 times, and you end up with well over 1,000 process steps for a single wafer. Etch and deposition together are half of all those steps, and there are plasma processes that are so complicated that is no fast exact physics model for them, so engineers tune them using data from real wafers. That idea, learning a process from data, is exactly where this course begins. Let me name the specific processes you will be seeing again and again in this course. Plasma-etch uses a reactive gas plasma to carve material away. It is our running example, and the earliest AI in fab papers we will read about are all about etch. Deposition in three flavors called CVD, PVD, and ALD grows thin films, sometimes one atomic layer at a time. Lithography prints the pattern with light, now using EUV. CMP, which stands for chemical mechanical planarization, polishes away the layer flat before the next. And ion implantation fires dopant atoms into the silicon to control where it conducts. Every one of these runs many times per wafer and produces a flood of sensor data, and that data is what the machine learning models in this course will learn from. Building at the atomic scale is only possible if you can also measure at the atomic scale. So here are the measurement and inspection tools you will work with. A CD-SEM is an electron microscope that measures how wide a feature is, its critical dimension. AFM, atomic force microscopy, drags a tiny sharp tip across the surface to map its three-dimensional shape. Scatterometry shines light on a repeating pattern and works out the shape from the reflection quickly and without damaging the wafer. Optical and E-beam inspection scans the whole wafer, hunting from defects. Ellipsometry measures how thick a film is from the way it changes polarized light. And virtual metrology, which becomes a big theme later, uses machine learning to predict a measurement when actually measuring each wafer would be too slow. We'll build models on exactly this kind of data: microscope images, measurement numbers, and sensor traces. Building and measuring have advanced together for 40 years, and this timeline from Research Institute IMEC shows it. In the earliest era, simple optical microscopes were enough because the features were large. As features shrank, new materials arrived, and engineers needed extra techniques to see them. When the transistor went three-dimensional with the FinFET, they needed new ways to measure three-dimensional shapes, and in today's EUV era, features are too small that random statistical defects appear, and the measurement tools now use AI to clean up noisy images. The lesson is simple. Every time we invented a new way to build a chip, we also had to invent new ways to see it. So where is all this going? On the manufacturing side, the roadmap keeps pushing in every direction. New lithography, new transistor shapes like CFET, memory going fully three-dimensional, and clever tricks like delivering power from the back of the wafer. All of these make the chip harder to build and harder to measure. And the newest tool showing up across the fab is AI itself. It is already inside measurement tools, cleaning images, predicting measurements, and it is spreading into every step. This is exactly the subject of this course. This is the detailed version of that feature, again from IMEC. Across the top are the years and the technology nodes running out to 2039. Each row is an entire area: lithography, logic, memory, and packaging. And under each one, you can see the specific measurement challenges coming: measuring taller stacks, seeing buried features, checking curved shapes, and inspecting the whole wafer fast. You don't need to memorize any of it. The point is the sheer breadth of what has to be measured over the next 15 years, and every one of these challenges is a place where AI can help. Here is the frame for the whole course, and it is a loop. Semiconductors are the hardest and the most precise thing we make. Because they are so powerful, they are what every AI system runs on. Chips power AI, and now that same AI being turned around and used to help design and build the next generation of chips. So the two feed each other. Better chips make better AI, and better AI helps make better chips. Today's lecture has two parts. Part A looks at where AI is entering the fab right now through 6 trends and 1 detailed case study. Part B asks whether the industry has actually been doing this all along by looking at its history. Let's take the first direction of that loop, where AI is entering the fab today. Here is the manufacturing line that we just described, drawn as a flow. The important idea is that AI does not appear at a single point, it shows up at many steps at once. At lithography, it helps control the process and predict defects. At measurement and inspection steps, it detects defects and predicts measurement. At final test, it helps improve yield, and running underneath all of it, digital twins and predictive maintenance watch every tool. The badges on this diagram match the 6 trends that we are about to walk through. Those entry points group into 6 recurring trends, and this is the menu for one tour. 1. Detecting defects and inspecting wafers. 2. Virtual metrology and improving yield. 3. Digital twins of tools and whole fabs. 4. AI inside lithography. 5. Predicting when the equipment will fail. 6. The AI factory that ties everything together. We will take them all one at a time, and for each I'll show you the idea and the real example. Trend 1 is defect detection and wafer inspection, and it is the most mature use of AI in the fab. A wafer holds thousands of chips, and you need to find the small fraction that has defects. Those defects show up as a pattern on a wafer map that marks which chips passed or failed, and in the microscope images of the surface. The job is to recognize and classify those patterns automatically. It's hard because defects are rare, there is a huge amount of data, and doing it by hand is slow and varies from one inspector to the next. How is it solved? The field moved through 3 stages: handwritten image rules, then classical machine learning, and today deep learning, mostly convolutional neural networks, the same kind of model that recognizes objects in photograph. A practical challenge is that defects are rare, so the data is very unbalanced, and teams handle that with tricks like generating synthetic defect examples to train on. The payoff is real. An automated system that classifies dozens of images per second, where a skilled person manages about one, and it does it consistently. The honest open problem is catching defect types that model has never seen before. Detecting a defect assumes you can see it in the first place, which brings us to measurement and inspection, the quite and essential other half of the fab. You are measuring features far smaller than the wavelength of visible light. To give you a feel for seeing it, finding 110 nanometer defect anywhere on a 300 millimeter wafer is like spotting a single dinner plate somewhere across the entire United States, and the fab does it on every wafer. Engineers use the whole toolbox we met earlier, the CD-SEM, AFM, scatterometry, and more often combined together. The slide is really why the next ranks exist. Measuring everything directly is expensive, so we look for a smarter way. The smarter way is trend 2, virtual metrology. Real measurement tools are slow and expensive, so fab can only measure a sample of wafers and hope the rest are similar. Virtual metrology trains machine learning models to predict each wafer's measurement directly from the equipment sensor reading, things like temperature, pressure, gas flow, with no extra measuring steps. That prediction feeds a control loop. The model estimates how the wafer turned out, and the controller adjusts the recipe for the next wafer before the process drifts out of the spec. So sparse that after the fact sampling becomes continuous, wafer by wafer feedback. What does that buy you? Because every wafer now has a predicted measurement, you catch the process drifting the moment it starts instead of waiting for the next sampled wafer. Tighter control means less variation, fewer scrapped wafers, and new products reach good yield faster. One industry case reported around 20% higher yield and 40% fewer defects. I treat those exact numbers as vendor reported rather than gospel, but the direction is solid. The catch is to remember a predictive model is only as good as its sensor data, and it drifts over time, so you will still need occasional real measurements to keep it honest. Trend 3 is digital twins, and it is the biggest theme in the industry right now. A digital twin is a live virtual copy of a real system, a single tool, a process, or an entire fab kept in sync with sensor data. You can use it to simulate, predict, and optimize the real thing. There are 3 scales: the twin of one tool or chamber, a twin of the process that virtually fabricates the structure before you run a real wafer, and a twin of the whole fab that models how material and work flow through it. Key feature is the live two-way link between the physical system and its virtual copy. Here it is in practice, and I'll frame this carefully as what each company reports or what these tools are designed to do. Lam Research says its etch tool can monitor and tune themselves with machine learning, and it reports using virtual tool models to help shorten development cycles. Applied Materials has built virtual copies of its equipment that can be used for process development and for sustainability studies. Intel reports using high-speed simulators to help plan and schedule across multiple fabs. Bosch has described a fab-level twin it can use to test changes before making them on the real line. The payoff they report include cutting months of tool development and large gains in efficiency. The hard parts, honestly, are getting all these systems to talk to each other and keeping the data secure and dealing with messy factory data. I want to slow down on one result because it is the clearest humans versus machine story in this field. Lam Research built a virtual process game, a realistic simulator of a plasma-etch, and used it to compare human engineers against AI algorithm at the task of developing a working recipe. The goal is to hit the target result at the lowest cost, where cost means wafer and tool time. The reason this is a genuinely hard for AI and worth studying is that the experimental data is scarce and expensive. You cannot just generate millions of cheap examples the way you can in a video game. Here is what they found. Human engineers were strong in the early rough tuning phase because they bring intuition and experience. The algorithms were strong at the end, fine-tuning near the target where they are very efficient. On their own, the algorithms actually struggled to beat the experts because they wasted experiments exploring with no starting knowledge. But when the two were combined, the human does the rough tuning first and then hands off to the algorithm to finish. The cost of developing the recipe dropped by about half compared to experts working alone. The lesson is that the win came from pairing human judgment with machine efficiency, and the paper is honest that getting people and algorithms to work together is as much a cultural challenge as a technical one. Trend 4 is AI inside lithography, the step that prints the pattern, and this is the hardest and the most expensive step in the fab. AI helps in two places. Before any wafer is made, we have to compute the photomask because light bends and the mask cannot simply be the pattern you want. So you have to solve for the mask that will actually print correctly. The computation is enormous, and it is where GPU and AI come in. Then during printing and machine learning watches the tool sensors and resulting images to predict tiny random defects and correct the process. At the cutting edge, EUV, the physics is partly random down to individual photons and chemical reactions, so this becomes a prediction problem. In practice, the headline is NVIDIA's cuLitho, which puts that heavy mass computation on GPUs and speeds it up dramatically, reported at 40 to 60% faster, and it is already in production at TSMC and Samsung. On the inspection side, teams combine several data sources, electron microscope images, optical images, and scanners' own sensors to predict those tiny EUV defects and adjust the process in real time. The honest limits, computation is still huge, the defects are random, so you are predicting probabilities and you need large and carefully labeled image datasets to train on. Trend 5 is predictive maintenance. A single broken tool can stall an entire production line, so you would like to fix it at exactly the right moment. There are three ways to do maintenance: fix it after it breaks, which causes the worst downtime; fix it on a fixed schedule, which is often too early or too late; or predict the failure from the data and schedule the repair at the ideal time. The third approach reads thousands of sensor signals from each tool, power, gas flow, pressure, vibration, and estimates how much of its useful life is left, so you act just before something fails. The economics here are dramatic because tool time is so valuable. A rule of thumb from McKinsey is that every hour of planned maintenance saves 3 or 4 hours of unplanned downtime. Better maintenance lifts equipment availability by more than 15%, and avoiding a single unnecessary maintenance cycle is in an advanced fab can be worth around $21 million a year. For context, tools run at about 30% efficiency 30 years ago and now run about 80%, and the data-driven maintenance is a big reason. Honest caveats: you need good sensor histories and records of past failures. Every tool type needs its own model, and there is always a trade-off between false alarms and missed failures. Trend 6 pulls everything together into what people call an AI factory. This is the computing and the software layer, a lot of GPU workhorse, plus a whole fab digital twin that hosts and connects all the trends we have covered. Think of it as the shared platform that defect detection, virtual metrology, digital twin, lithography computation, and predictive maintenance all run on and feed back into. The message is that the field is moving from scattered point solutions toward one instrumented AI coordinated fab where data flows continuously between physical line and its digital copy. Here is a concrete version. NVIDIA and Samsung announced what they call an AI mega factory, tens of thousands of GPUs with digital twins spanning Samsung's fab to speed up everything from design to daily operations. A specific checkable case putting cuLitho inside Samsung's max computation flow sped it about 20 times. And this is happening across the industry with TSMC and SK Hynix building similar fab twins. As always, treat the exact vendor numbers as indicative and note that this approach takes enormous money and data infrastructure. That is where AI is entering the fab today. That is the present. Now let me ask a fair question. Is any of this actually new? The industry often says it has been doing AI forever. Let's test that claim by looking at the history. The timeline shows that machine learning has been shipping into real fabs for about 30 years. In the late 1980s and 90s, neural networks were used for process modeling and fault diagnosis. In 90s and 2000, control loops with learned models became routine. In the 2000s, systems detected faults from sensor data and inferred wafer measurements. Computational lithography, which we just discussed, arrived in 2000 and 2010s. In the mid-2010s, deep learning took over defect classification. For decades, AI in the fab meant learned models sitting inside the control loop doing one job well, real and valuable and narrow. Let's look at the very first examples. The earliest papers are strikingly modern. In this 1991 study from Berkeley by Nadi, Agogino, and Hodges modeled the deposition process called LPCVD, predicting things like film thickness and stress from process settings. Their approach combined two ideas. First, an expert drew an influence diagram, a simple map of which inputs affect which outputs, which cut down how much data you need. Then neural network learned from the actual numbers. They even ran the model backwards to design new recipes for a target result. It is a hybrid human knowledge and machine learning, an idea the field keeps rediscovering. And here is what they proved. The comparison was against the standard method of the day, which built models by statistical curve fitting. On predicting deposition rate, their approach had about 1.5% average error versus 5.1% for the standard method, roughly 3.5 times more accurate. On the harder quantity, film stress, it was about twice as accurate. It achieved that while training only half as much data. Scatter plot shows it. Their model points hug the ideal diagonal line, while the older method scatters around it. Their honest caveat is that this is a small study and they say machine learning should work alongside statistical methods, not replace them. 2 years later, a follow-up study from Georgia Tech ran the cleanest version of this experiment. Himmel and May took a plasma-etch process that had already been modeled the standard statistical way, a trained neural network on the same kind of data, and compared the two head-to-head. The neural network was more accurate and it needed fewer wafers to get there, and in the fab, wafers are the budget. The honest limitation, which they state clearly, is that this was one process, one chamber, a handful of knobs, and the advantage did not automatically carry over to the next chamber. To say why the network won't, they lay out the problem plainly. Here is the problem in plain terms. On this etch tool, you set 6 knobs: the RF power, the chamber pressure, the electrode spacing, the 3 gas flows. From those, you need to predict 4 outcomes: the etch rate, how uniform it is, how selective it is, how straight the etched walls are. The relationship between the knobs and the outcome are very tangled. Every knob interacts with the others, and there is no physics model fast and accurate enough to run inside a fab. So the map from the settings to results has to be learned from the real wafers, and every wafer you run costs money. That is why fewer wafers is the number that really matters. First, how this was done before machine learning with a method called response surface methodology. The workflow is disciplined. You fix your knobs, their ranges, lay out a design set of experiments to cover them efficiently, run those wafers, and then fit a simple polynomial, basically a smooth curved surface, to the result. It works, it gives you the real understanding of the process. Its limitation is baked in from the start. You decide the shape of the model, a quadratic, before you see any data. So when the real process has a sharp threshold or flattens out, the model cannot capture that no matter how many wafers you add. Widening the knobs range means starting an experiment over. Now here is the machine learning version. A small neural network, 6 input feeds into the hidden layer, which feeds 4 outputs, and it learns by a method called back propagation on the same experimental data. The important shift is that you do not decide the model's shape in advance. The network discovers the relation and stores them in the internal weights, including the interaction between the knobs. The cost moves from the wafer to the computer time, and even back in 1993, that trade already paid off. The new problem it created is that the network has its own settings, like the learning rate, with no theory to pick them, so a follow-up study used the same design of experiments idea on the network itself. So how much did it actually buy? Two things. It was more accurate across 4 outcomes, and the part that mattered commercially, it reached the accuracy using 18 fewer wafers than 53 the older method needed. In a fab, each of these wafers is a real money and tool time, so the saving is the headline. The paper closes with an honest point we'll keep coming back to. The accuracy gains was real, the wafer saving was real, neither one automatically survived moving to the next chamber. Let's be precise about what that early AI really was and where it hit a ceiling. Its strengths: it learned from a narrow task, from very clean, well-labeled sensor data. It lived inside a tight control loop where the loop did most of the work and it was restrained whenever the tool drifted. Now, every new tool or fab meant starting over from scratch, nothing transferred from one setting to the another. The model could not be combined and reasoned about, and the knowledge stayed locked inside the model. No engineer could really interrogate. Those exact limitations, transfer, composition, interpretability, are what today's methods are starting to break. The limit didn't stop deployment though. Through the 1990s and 2000s, learned model became routine fab infrastructure in 3 different ways. Run-to-run control, put a learned model inside the feedback loop to adjust the next run, and that is the ancestor of virtual metrology that we saw earlier. Fault detection used machine learning on sensor data to catch equipment problems, the ancestor of predictive maintenance. And virtual metrology itself, predicting wafer state from signals, was deployed 20 years ago. Today's new applications actually have deep roots in production. The deepest deployment of all was in lithography. Long before anyone said generative AI, making a chip already depended on massive computation to design the photomask. The mask correction steps we discussed under Trend 4. This has been the critical path to manufacturing for 2 decades. And here is the straight line to today. Those computations were always limited by computing power, which is exactly why GPU acceleration like cuLitho landed here first and gave those 26 times speedups. The mid-2010s brought the deep learning wave. Once convolutional neural networks broke through an ordinary photographs, fab had an obvious data-rich target waiting, wafer maps and inspection images. Deep networks took over defect classification at full production volume, and that is exactly where Trend 1 from Part A began. It was a clear step in capability and working on richer data. It was still narrower, 1 model per fab, retrained on drift with same structural limitations from a few slides ago. That sets up the real question: what, if anything, is genuinely new now? Here is the honest answer. Yes, in 4 specific places. First, surrogate and generative model that stand in for whole simulations rather than fitting one step. Second, pre-training and transfer, where representations that learn once and reused across tools and nodes exactly what old approach could never do. Third, reinforcement learning inside chip design, where tools like Synopsys, DSO.ai now do chip layout in ways that break from hand-tuned rules. And fourth, agentic and language interfaces, systems that chain multiple steps together and let you ask questions of fab data in plain English. These are capabilities that let modern AI build on itself where the old approach could not. Here is a counterintuitive punchline of the whole industry. The thing holding this field back has been the data more than the algorithms. Fabs are the most heavily instrumented factories on earth, yet the data is hard to use. It sits in silos with design, lithography, etch, measurement, test all in separate systems. Much of it is proprietary, owned by tool vendors. It is largely unlabeled because the ground truth arrives weeks later at final step and rarely points back to which step caused the problem. It keeps shifting because every chamber, every production run is a little different, abundant and barely usable. That gap, not the math, is what AI for semiconductors has really been up against. So as you read all the claims you will meet this semester, hold two ideas at once. First, the industry really has used AI for decades, which is a useful corrective to the breathless hype, though the same fact can be used to wave everything away as nothing new. Second, the real bottleneck is in data infrastructure, which is largely true and which is also conveniently the sales pitch for companies who say it the loudest. Both things can be true at once. The habit I want you to build is to ask every claim, why does it actually let us do and who benefits if I believe it? That critical eye is exactly what we need for the last part of today, where this is all heading. Let's look forward. Today's AI tools are mostly what people call co-pilots, assistants that help with one piece of the task while a human stays in charge. That industry now wants to move towards an agentic system where several AI agents coordinate under a manager and make decisions on their own. That move keeps stalling, and the reason is data. A chip is made over 1,000 steps across many different systems, design tools, inspection, the factory's execution system, test, piles of engineering notes, and each one keeps its data in its own silo. Human cost is real. An engineer can spend a full quarter of the year just gathering and cleaning data sets before building anything. This connects straight back to part B, where we saw the bottleneck has always been the data. And the scale of the data is staggering. In a single large fab, every minute brings about 95 gigabytes of equipment data. Over a full day, it adds up to petabytes. That same minute holds 75,000 wafer movements, 15,000 sensor readings, and hundreds and thousands of recipe events. Around all of that sit big pressures, equipment spending rising past $150 billion, a need for 1 million more skilled workers by 2030, and a growing share of cost in the final packaging and test steps. So the data is not missing at all. It is fragmented and hard to use, the very same gap we saw in the history. The proposed system is called a unified data fabric, a shared layer that connects design, manufacturing, test, and packaging in real time, so those AI agents can actually reason across the whole line. It rests on 4 pillars. First, fast shared access to data at massive scale, standard labels on data, so you can trace the problem back to its cost, keeping the computing close to data so you are not constantly moving it around, and strong security and governance. There is a real tension here. Cheap companies are cautious about the cloud for security reasons, yet they cannot meet the computing demand on their own machines alone. The proposed way through it is to protect the data itself so that the security travels with it whenever it's processed. Here is a concrete illustrations. Elon Musk's idea of TerraFab puts design, fabrication, test, packaging all under one roof. My reading is that this is really an argument about data continuity. With everything in one place, you get one connected data set, a fast improvement loop. Only a brand new fab built from scratch can pull it off, which would make it a blueprint from the future. When the shared data plane like that this works, it unlocks the payoff we have discussed all lecture. Automatic process control, predictive maintenance, virtual metrology, smarter scheduling, faster defect fixes, and a higher efficiency. In other words, the 6 strands from part A all running together at full fab scale. Which brings us to the closing point. This cannot be built by one company alone. It takes the whole industry working together, the equipment makers, the fabs, the design tool companies, the data infrastructure providers, and the standards body to agree on common data labels and a shared trusted picture of what is happening on the line. This is my one-line summary on the slide. Without a common data plane, there is no autonomous manufacturing. This is the next chapter of the two-way street we opened with, and this is exactly the kind of problem I hope your semester project could take a piece of. And this is the end of lecture 1.